All right, let's move on to 9.1b. So here we're going to talk about the graphs of a polar equations. So last time was like polar coordinates and graphing those, but here's an equation. So talking about a polar equation, what we're going to look at here is this is an equation, so it's going to have an equal sign in there that is expressed in terms of polar coordinates. So that's what we kind of discussed in 9.1a was the coordinates. So an example of that would be like r equals 2 sine theta, right? You've got your r value, right, because that was part of it, and then you've got a theta as well. So when we have an r and a theta in there, in the equation, that would be a polar equation. Okay, a polar graph. This is the set of all points in which a coordinate has coordinates r, comma, theta, and that satisfies a given polar equation, right? So when graphing these equations, we're going to basically include all points that make a true statement. So you're looking at using these r, comma, theta points, and it satisfies that. So when we're graphing, we're going to include all points that make this a true statement. What that does is it usually makes this a circle or a line, depending on what we've got. Okay, so that's one thing we'll talk about later on when we get to the examples. Another concept we're going to talk about is the polar distance formula. So you can see that if we've got, say, P1 here, which is R1 theta 1 right here in the example, and we've got P2, which is R2 theta 2 over here, we can find the distance between those two given by the formula. So this distance here would be given by this formula right here, okay? So what you'll notice, though, is it looks very familiar. It's square root, and then it's basically the law of cosines. So you've got R1 squared plus R2 squared minus 2R1 times R2 times the cosine of the subtraction of the angle measures, theta 2 minus theta 1, okay? So just kind of look at that, right? This is all law of cosines minus the square root symbol, but it's just like you got one thing squared plus another thing squared minus 2 times both of those times the cosine of something. Well, in that case, we're just going to subtract the angles to get that. So if you got your R1 and your R2, then you're in good shape, and then you can just subtract these measures to get an angle measure to pick the cosine up. And then just don't forget that you've got to take the square root of it at the end, okay? So very similar stuff that we've done before. So let's get to some examples here. And this is a short and sweet section, so we can kind of just get through it here. So graphing each polar equation here. This first one, very simple one, r equals 3. So basically we're looking for all points that make this a true statement. Okay, so if I look, right, r is 3, that means my radius would be 3. So if I just go out to like here, from the center, right, here's my center point. If I go, let's just go out on a 45-degree angle here. 1, 2, 3. There would be a point there, right? And that's what pi over 4. If we use it in radians, that would be the point 3 pi over 4. Or, right, 3 45 degrees, right? Okay. And then we took that, all points that r is 3, so that actually would go all the way around this circle here, would be all the points that have r equal to 3. So I just made that one point there, and maybe just pick another one here, like pick an easy one, right, at 180 degrees. So if we wanted to go in radians, that would be 3 comma pi, right? So that's basically it. Like we said, in that case, it's where it looks like a circle, like we said above, okay? Typically, it's going to result in a circle or a line. So let's do one where it looks like a line. In this case, we're in radians. Notice the difference. Here we have r equals, and we get the circle. Here we have theta equals, and this is where we're going to get the line. So now we're looking at what 2/3 pi is. Well, what is 2/3 pi in terms of degrees? Because we have degrees on our graph. So because of that, if we look at all our graphs, these are all in degree measures. It might be helpful to actually turn this into degrees, which if I do that, if I multiply by 180 over pi, right? These pi's are going to cancel out, and I'm going to get 120 degrees. So that might be helpful since we have all degree measures here. So now I'm looking at this being along this 120 degrees. So this whole thing, 120 degrees, that is going to be all the values of 2/3 pi, right? So I could pick a point up there and say, like this point here, let's just go up, let's say 1, 2, 3, 4, 5, right there. That would be the point 5, comma, 2/3 pi, or 5, comma, 120 degrees. Depends what they want the answer in, right? If they don't say, then I'm guessing you put it in radians. All right, so that would be that one. So all the points along there. Now, we also have to remember that this can extend the negative versions, right? So that means that if we extend that through the other direction, through the center point, right? So if I take this line here, but I keep going through the center to the side opposite, kind of at 300 degrees here, okay? These will all be negative versions of that point, right? Because remember, negative takes that angle measure and then goes to the opposite side. So if we pick a point like, say, over here, and let's do one in between the lines. So we got 1, 2, 3, 4. Let's do 4.5. So 4 right here. This would actually be negative 4.5. Because remember, negative takes that angle and then flips to the other side of center. So it goes over here. So negative 4.5, comma, 2/3 pi. Okay? So that's how we can graph those. Again, just notice that we've got an r equals here. So that's a radius. And we get circles for our graph. And then theta, that's the angle measure. So we're talking about everything that is that angle measure. And you get a line for a graph there. All right. That should help you out a little bit. All right, the third one, we're actually going to use that polar distance formula. So I'm going to just skip up because we're going to have to draw a graph here. So we've got a boat question. Naval radar is tracking 2 aircraft carriers. The coordinates of the 2 carriers are as follows: 8,150 and 365. R is measured in miles. Okay, measured in miles. So radius is in miles. So sketch a graph of the situation. So just sketching one quickly. And it's not going to be pretty because we're drawing circles. But if I start here with my circle here, my polar point here, that's 1. And then if I kind of go outward, again, like I said, it's not going to be pretty. That's 2. We can go 3 out here. Do the best you can. I'm just sketching. And actually going to go by 2s just because I'm running out of room. Okay. And I think I did one more maybe. Okay, I got room for another one. Let's go ahead. Obviously, it's not a perfect circle, but deal with it. Okay, so again, if we start with our polar axis, our initial ray, so if I take that here and go out to the right from the center point going out to the right, okay, I can label some of these things. And like I said, I'm going to go by 2s. Each line is going to be worth 2 just to kind of help us here. So that would be 2, this would be 4, that would be 6, 8, 10, and 12 out here, okay? And then I could kind of make also marks to be degrees here. So I'm going to go back to black on the grid. And, you know, if I know that straight up is 90, right? And then I know that out here is 180 degrees. Okay, I can kind of get those easy ones in here, 270. I know this is 0, okay? And 360. All right. So then I can kind of draw a couple in there if I just kind of split it into thirds. So if I take this one out here and this one here, I could say it's not pretty, it's not exact, but 30, 60. And same thing here. I can go 120, 150, and so on and so forth. Just kind of split them in thirds. Now I've got my little spider web graph that I can work with, okay? So now we want to graph these points, all right? So I'm going to graph them in green just to show them a little bit. And so the first one is 8 and 150. So I'm looking at 150 degrees with a radius of 8. So that's going to take me out to the fourth line here because I went by 2s, 3, 4. And I'm going all the way up to 150 degrees on 4. So here's 150 degrees. Again, 2, 4, 6, 8 would be right here would be that point. And we'd say 8, comma 150 would be that one. So that's point, the first point. Second point is 3 and 65. So there, I'm looking for 65. Well, 65 is not right on the line, but it's going to be close, right? So I'm going to go a little bit to the left of this line here, and 3 is between 2 and 4. So here's 2 and 4. So I'm going to probably be right around here, right? It's going to be in between the 2 and 4 mark, and a little bit to the left of this line here. So my point here would be 3 comma 65 degrees. Okay, so next part, that's part A, just kind of doing the sketch. Okay, so now part B, what is the distance between the two aircraft carriers? Okay, so I'm looking for the distance between these two things from right here to up here. That's what I'm looking for, is for that distance there. All right, so to do that, I'm going to use my polar distance formula right here. Okay, so I'm using that, and so I'm going to say my distance is equal to the big giant radical sign, and I've got my R1 and R2 is going to be 8 squared plus 3 squared minus 2 times 8 times 3 times the cosine. Now, what's the cosine going to be? Okay, right? So, because my formula, again, is R1 squared plus R2 squared minus 2 times R1 times R2 times the cosine of theta 1 minus theta 2, or vice versa. I can really do that either way. That could be theta 2 minus theta 1. I just got to get whatever's going to give me a positive angle measure. So in this case, we can see that we've got 150 and then we've got 65. So when I do that, I'm going to go 150 minus 65 is going to give me 85. So I'm going to do the cosine of 85 in there. And then I can punch all that in the calculator just like allow cosine should work for you. Take the square root at the end, and you're going to get about 8.3 miles. That's what we're dealing with, miles. Okay? So that's a short and sweet lesson on graphing polar equations. We'll see you next time.